All right, so in last lecture, we went through this whole example about pointers and pointing to addresses and where different pointers point, right? And the whole point of it is that we had this single bit full adder, right? And we're trying to return two values, and when you want to use pointers to make that more efficient. And so now we have to deal with actually using functions with pointers. So there's two important things that you need to know: passing by value and passing by reference. I had a student make a note on a TGOs. I should point something out. Whenever I have just the TGO, and you know sometimes I'll say end 3.10 or end 3.11, and other times I won't. If it's like this, what this means is and there's no end here, what that means is that's a definition. I can tell you 3.5 is defined passing by value, or 3.11 is defined passing by reference. If you're confused about that, go to the Blackboard. All the TGOs are posted there, and you can see it. Those should clarify things for you. So 3.10 is passing by value. It tells the compiler to make a copy of the value in memory for the variable's value to be used by the call function. Any changes to that variable's value are not affected in the calling function. So what that means is, if I have IEEE convert and I pass a value by if I pass a variable by value, and it changes that value in the calling function, if I go back up to main, the variable will still possess its initial value. Whereas with 3.11, if we have passing by reference, which passes the location of the pointer in memory to the function, any changes to that value in the function does change it in memory are affected in the calling function. So if I have a pointer P1 like we covered last class, right? And that's pointing to variable x. If I pass P1 by reference and the function updates that, it's going to update the value and it will change it in main. So sometimes this allows you to, if you want to take a variable copy and you're doing some sort of value and it becomes unavoidable, but you want to retain that initial value, you can pass by value. Whereas passing by reference, or more importantly, you want to guarantee that nothing will change, pass by value. Whereas passing by reference, changes will occur. So here, the best way to do this, if we're applying it to our one-bit adder, is you have a carry in and a carry out value, right? So you can reduce it by saying I want carry in, and I'm going to have the pointer carry out updated, and then pass it back. So that's one way you can reduce the number of variables. And we start talking about registers in the data path and trying to allocate those properly and minimizing the number of registers you're using. That actually becomes important. So to talk about this more clearly, so here we were talking about last lecture about we have these values and we have these pointers and we update the values here. What happens when we try to compile the code is that we get warnings and not errors. So here I have not allocated, I've commented these two lines out that we had last time where they say, all right, P1 is pointing to the address of X and P2 is pointing to the address of Y, right? So I've commented those out. And now I'm trying to run that same fprintf. So what happens is we're going to get a 32-bit value. It's the same thing. We had IEEE 754 errors if we're using floats instead of integers. Now we're getting the numerical value of an address in memory. So if I run this code, comment these out, and print them out, here's what's going to happen. I'm going to get warnings, not errors. And then when I do my initialized values, what's going to happen is I'm going to get 100 and 200 like before, but then fprintf with P star 1 and star P1 and star P2, it's going to give me negative 998029168 and 10884016. So what do you think those values are? I mean, I've given you a hint with the diagram, but what do you think those values are, and why would I get a negative number for memory?
distance from the base pointer.
Bingo. Well, okay. So what does that mean, distance from the base pointer, other than you can read?
I mean, it could go one direction or the other.
Okay.
It's like negative.
I take it none of you have taken operating systems, right? Okay. So basically what's going on here is the operating system has to allocate memory somehow. So what's going to happen is during the course of a program, the operating system isn't just running your code. It's running being able to contact memory. It's being able to program that interfaces with your monitor. It's running a program that interfaces with my USB. It's running Word. It's running any kind of Internet Explorer, or Internet Explorer is dead, RIP, but if you're running Chrome or Edge or anything like that, your operating system is going to be doing a number of tasks simultaneously. And so what's going to happen is it has to swap memory in and out. And that's why your computer starts slowing down after you run for a while, because it can't swap it out while something's pointing to, while you have a pointer in memory that you haven't deallocated. And we're going to get into allocation and deallocation of pointers soon. So what's going to happen is I have the base pointer of the program, the operating system has put it in here, and I have my local copies X and Y in memory. And these point to the registers, and we'll get to program counters later. And then what's going to happen is I have functions, and I need to put the functions somewhere in the memory, right? So in this case, when I did this run, what happened is the operating system put this pointer here, and then allocated this pointer here above the base pointer. So when we get into load word and store word, I've kind of talked about these briefly, but I have this load word, and it's going to be, I'll just say S0, comma, and we'll call it 16 S1. So what this instruction means is I have a register, S1, that tells me the exact number of the base pointer in memory. And then we're doing something in MIPS called byte addressing, which means every address points to an 8-bit value. So if we have a 32-bit value, that means I need to put 4 of them together in order to create one 32-bit value. So each of them is going to represent 4. So if you're doing an array, that means our 0 value means give me the first value in the array. So this becomes 0, and I can tell you 16 is going to be, if this was array A, right? This would be A of 4. So basically, load word is telling me, go to this base pointer, go down 16 blocks, get me the next 4 blocks, and then put them in the local copy of the register indicated by S0. So that number 16 corresponds to the offset. This same value, the distance from the base pointers, are your offset from your base pointer of your program. So that's what those values are indicating. That's telling you an actual physical location in memory. So if you get something like that when you're testing your function and you get some large number, oh, I'm not pointing to an actual value. I'm pointing to I'm pointing to somewhere in memory where I haven't indicated what it is yet. So when you do this, P1 equals ampersand X, right? What that is physically doing is changing this number to the offset from the base pointer to where X is. So now it's pointing here, which is why when you then do star P1, it's dereferencing it and it's telling me, tell me the value that it's pointing to. So that's what a pointer is physically doing. And that's why you're getting that error. Okay, so then I add so therefore to use pointers in function calls, you must be precise. So I've come up with a handy 5-step way of properly declaring functions, calling the functions in the calling function in main, for example, what to do when you actually get in the function, and then when you come back. So step 1, when you're actually writing your function declaration, separate the variables you wish to call by value or by reference by determining which values you wish to change in the function. So if we're doing a full adder, so we'll just call it full adder, right? I'm passing in A, B, and C in, and then I'm getting sum and carry out back, right? So there's multiple ways to approach this. I would separate it. I always start, my convention is I would do A, int B, int Cn, comma, int, and we'll get to this stuff in a second, int sum, and then int Cout. And I kind of alluded to a way you can shrink this down for teaching it. I'm going to leave it like that. So step one, just okay, so actually this sums up step 1, 2, and 3. So in function declaration, write the variables you're passing by value first, as I have done here. And just indicate them. Do not put any stars or ampersands. That's where people start messing up when they start trying to experiment. Step 3 in the functional declaration, write the variables you are passing by value. I'm sorry, this should say by reference. I will update that in the notes. By reference, or I will, that should be by reference. By passing the contents of the address with a star, as I've done here. So I'm passing these by reference. And what that means is I'm making a copy in the function of the variables in the memory. So I have a block of the memory specifically for the function call. And we're eventually going to learn about something called jump instructions. So we're going to get to the function call in main. It's going to say jump to where the function is in memory. And that's where it's going to start. And where the function is in memory, it's going to have its own local copies that are going to load that value when you get there. Passing by references means it's actually going to contain the physical location. So the first thing we have to do whenever you get you have the dereference instruction, that's actually going to perform what's known as a load. I actually showed you a load word operation. Basically, you're getting in there, getting the value, performing your operation, and then your compiler will then put a store word will actually update that in memory automatically once you're done. So that's how you write it up. And then step 4, every time you call the reference variable, use star to dereference the pointer so you can update the value in memory. So basically, I'm going to be using AND gates. So you sum equals XOR A comma B. I think the shortcut way I did it was just XOR and then call XOR again. A comma B, okay, comma C. So here in this function, what I've done is star sum. I've updated the value that's going to be passed back to the calling function by calling XOR from gates.h that you guys we're going to do in section 2 and you're going to be doing as part of your project 1. Calling XOR again, A XOR B returns the bool here, which is then XOR with C. That value of bool, these should all be bools, by the way, not ints, now that I think about it. But the value will be updated by using the star sum. So it's going to get this value, and then what's actually going to physically do is going to do store word, and it's going to take the value, the temporary register, store it to the pointer in memory. All right, and then the last step is in the calling function, for every value you're passing by reference, use the ampersand. So if you're declaring bool A, bool B, bool C, bool sum, bool carry out, so you're doing bool A, B, C, sum, C out, right? And then you define them. And then you call FA. You're just going to pass A, B, and C as normal. And then sum, ampersand S. And then carry out, ampersand C out. And where this becomes valuable is we're going to learn how to reuse code to do 32-bit adders. So then, once you've updated C out, guess what that can be? C in of your next bit, right? For those of you who are familiar. And we'll describe that here in a second. Okay. Does that make sense? I'm going to show you an example. Actually, I've kind of gone through the example already, but I'll show it to you again. This is the graveyard where many a computer engineer and computer scientist has gotten lost and quit. And so I figure here's your algorithm. You follow that, you'll get it right 99% of the time. We'll get into where arrays cause trouble with that in a minute. Any questions? All right, so here's an example where I follow my steps. This time I properly defined that they were bools. So I defined bool and 1, XOR 1. So sum, as I indicated before on the board, this is the exact line of code. Star sum equals XOR C1 Cin. And then C out becomes and 1 and 2. So and or become your values, right? So then when I'm calling the function, so you see I did the same things. I put the values I'm calling by value, the variables I'm calling by value first, and then the variables I'm calling by reference second. Yes, Justin?
Now I guess for functions, you have to put an underscore before that.
That's my convention. I do that for gates. In this case, it's a full adder, so I can separate like physical elements versus functions I'm doing on it. For example, you saw earlier I just wrote IEEE 754 convert. That's a function that's actually doing something. I just do this as my own way. You'll discover your own conventions to name your gates to keep them straight, or to name functions is the things that you want to do. Oftentimes you'll see this underscore in front as a convention to separate how the coder is doing it. It's a good question, though. All right, so in this case, I wrote a function called full adder test. So here, I'm incrementing through all of the possible values, right? So here, what I'm doing is I've done Cin. I'm inverting it, so Cin inverts every time, every other time B inverts, and then every 4 time A inverts, right? So that'll give me my way of giving 0, 0, 0, 0, 0, 1. So these values down here, which I'll scroll up for those of you in the back in a second, give me my full range of testing. And then, as you can see, as I've indicated, in the calling function in step 5, I've passed the variables by value as normal, and then when I call them by reference, I use the ampersand. And then the next step, I print out my test case. And then this is the printed out results. As you can see, this is A, B, and C, and this is sum, which sum is XOR, so 0, 1, 1, 0, 1, 0, 0, 1. Which is that case, and then you get and or, so this will be and this will be or, 0, 0, 0, 1, 0, 1, 1, 0. So that is our correct test case. But the key thing is you saw how the function was called as I defined it here, right? Okay, so does anybody have any questions on that before we discuss passing arrays to functions? All right, so another place where people get locked up is in passing arrays to functions. Now, what is an array in memory? We kind of just went over it. Yep, exactly right. Just a block, right? And how do we indicate where an array is in memory? Yeah, pointer, right? We have some sort of pointer that we've indicated. So we have some sort of register containing a 32-bit value that indicates our base pointer. So where people get hung up on passing arrays to functions is they get this whole value of pass by value and pass by reference. So then what they try to do is they try to pass an array to a function by value. And then they do their code, and then they print out their test case, and it turns out the array has actually changed in the function, and they can't figure out for the life of them why. So you all now know enough to answer that question. I am a first-year computer science student. I'm struggling with C++. Why does this array keep changing when I pass it the function? I'm not using a star. I'm calling int array brackets. Why is it changing?
Passing the reference.
Exactly right. Because what exactly is the reference? The memory address in the register. That load word instruction, I showed you that, it has the offset. It's when it calls the function, it's just passing the pointer. So these are logically equivalent. If you're in main and you have int a bracket, right? And let's say we'll just call it 5, right? These are logically equivalent. If you do this, if you do void foo int int a as your first, or if you do void foo int star a, because they're both pointers. And this is where having compiler-driven encoding of the microengine becomes important. Because when you write this code, what's going to happen is the compiler is going to know that you are passing an array instead of just an integer. See right here, int star a and int star sum. In the case of the compiler, what's going to happen is the first thing it's going to do is it's going to add the offset of your array here. So if you called, let's say you do a of 3, what's going to happen is your compiler is going to multiply by 4. The 3 is going to get 12. That's going to add to the offset of the base pointer, and then get that value, update it, and then put it back in memory, right? Whereas if it's just a star and this is just one integer, the offset to the pointer will always be 0. Because it's just going to be those 4 blocks. So that's the difference. And that's where people get hung up. Does that make sense? Good. Very good. So since we're dealing with blocks of memory, we're going to talk about these 4 different functions. 1, 2, 3, 4. First things first, standard library.h, as I indicated in my email. I probably should have told you what that was. It's just the standard C library. You can use that to do standard error printing to the error stream for I/O. So as I told you in the email, I've included that as a topical guide objective. For 3.14, these are 4 different functions that are very important. So the first one is Malik. Malik stands for memory allocation. So here it says void star size underscore t size. Allocates the specific number of bytes. And I'll show you examples of all of these in a second. Void star reallocation increases or decreases the size of the specified block of memory, reallocates as needed. So a very common operating systems problem is I have a certain amount of memory and I have programs that run significantly larger than the amount of memory I have, right? Especially when you're dealing with, remember that PDP 14 that the computer is the size of the room and it ran on a megabyte of memory, but your program probably required a lot more than 1 meg if you're trying to do a sufficient program. So you had to worry a lot about memory allocation of your local cache memory. So this is where it becomes important. Memory allocation, reallocating memory. So in the process of reallocating memory, sometimes you need to move your pointer up or pointer down, which is why you get your negative or positive results. And again, it tells me where the memory array is. and tells me what I need the new size to be. So in one case, this is, I'm not going to go too much into detail on this, but this is a challenge known as paging or segmentation in operating systems. So let's say I had a block of array of 5 words, and I need to page it to 7. But my operating system is using those next 2 blocks of memory, right? So I can do one of 2 things. Either I can copy the whole thing and move it to another section, another page, or I can take another pointer and have the other 2 variables in memory point to those last 2 elements of the array. So you can see how it gets complicated very quickly. And there's pros and cons to each of those approaches. Now, Kallik here allocates the number of bytes and initializes them to 0. So here, if we had allocated our pointers to the array, and we had used Kallik, and we point to somewhere else, and we do fprintf, it's going to print 0 because there's an actual physical value there. So it's you get the number of items and the size. Now what that means is, let's say I want to use Kallik to initialize an array of bools, specifically 32. So I would do 32 and bool. A bool indicates it's going to take the size of this, multiply it by 32, and get all of that and initialize it to 0. And then last but certainly not least, and this will be a very useful function for all of you, void free pointer. Remember I was trying to do the demo where everybody's pointing. At the end, the first thing I do whenever I allocate a pointer or an array, the first thing I do is I go all the way down to the bottom of the function I'm writing, and I'll write free. So that way, once I'm done with that function, I've freed the pointer and I'm done with it. The very first thing I'll do. And so it releases the specified block of memory back to the system. So now the operating system has it to be able to use for other purposes. So now that we know allocation, we know all of this, we can actually write a 32-bit full adder. So now we've written a full 1-bit adder, we know pointers, we know functions, we know memory allocations. Now we can do this. Okay, one last thing, and I wanted to include this in here. Remember, in English, we read from left to right, correct? So when we read from left to right, we're reading this way. So our array is going this way, but our most significant bit is going to be on the right-hand side, right? So oftentimes, trying to get this bit, let's say we have our 4-bit value, right? And we're indicating 0, 1, 0, 1, right? We know that this is the least significant bit, and we read that way to add, correct? However, if I'm allocating an array, I'm still going to read left to right. So this is going to be array 0, 1, 2, and 3. So oftentimes you're either going to be, this is where knowledge of for loops is going to come into play, and I'm going to show you an example of this. So so here, if I were trying to calculate this value, I know the length of the array is 4, right? And I know that here I need to add 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0 times whatever the values are, right? So to loop through this array, what I would do is I would go for I equals 0 through I is less than 4, I plus plus. Then I have this value of I corresponds to this. So then I could have, and let's say I call this a length equals 4. So then I could say 2 to the, if I had math.h included, I could do length minus I. So that gives me 4 minus 0, which is 4, right? But I'm still off by 1 because we started. So I could do length minus I minus 1. times, or you can even, what I probably did is it was if A of I is true, then add this to the current value, right? So here would be, it's false, so we won't add. Then we get to here, so it's 1. So it's 4 minus 1, which is 3, minus 1 is 2. So this becomes 2 to 2, plus 2 to 0, which becomes 4, plus 1, which is 5, so we get the right value. So that's another place where people get hung up. And what I'm guessing is that a couple of you will write that on your challenges for your project. But okay, so here I've included mips arith.h because I'm using gates, because this is an actual arithmetic.h file. I included one other thing, pound define. Pound define allows you to define a constant value using a variable. So in this case, let me read the rest of it before I go. This allows you to only need to change the value in one location instead of in many functions and files. So for example, let's say here we're designing a 32-bit MIPS data path. You want to make it 64 bits, right, for whatever reason. You can either go through all of your files and change everything, or you can design it in such a way where you only really need to change this to 64 and everything else extrapolates out. These pound define are very useful. Another thing, no semicolon after pound define in your .h files, or even in your .c files. If you do that, you'll get error messages. So here I've defined a new header file, mips arith. I have included gates.h and standardlib.h. As somebody pointed out, use quotes for your user-defined header files and brackets for GCC header files. And then now we can implement our full adder. I have written a function in my header file of bool star 32a. Bool star I've indicated is carry out. So I have two inputs of 30 of bits length, and then I return a sum, and then I actually use the carry in to represent the carry out, because what we're going to do is we're going to be looping through it. The carry out of the bit is going to become the carry into the next bit. So here, to test the 32-bit full adder, I have my inputs, and I have my sum. Here I have used Malik. If I did Kallik, so basically this void pointer, you do bool star, so now you have a pointer to a set of booleans, and I'm allocating 32 bits, or 32 bools. So that's what that's doing. If I did Kallik, it would be bool star CALLOC, and then it would be bits bool, right? And that does the same thing, except it initializes them all to false. I didn't do that because in my function I'm going to be updating all 32 values. We're already at 10:45. Let me go through this, and then I'll. The homework ends at 3.15, so 3.10 through 3.15. That's a pretty easy weekend assignment, right? I'll explain the full adder code, and then you're dismissed after I describe it. So go away. So I have my inputs, bool A and bool B. This is where defining preconditions and postconditions becomes important, because now you know that they're arrays and not values, so that when you write the code, you pass the right things. So I've now allocated an array for sum, and then I initialized I. I've done this for loop in a way. I equals bits. I've gone backwards this way, and now I'm adding them all. So I start at 0 for both of them, and I carry on like this. So I'm starting at the end of the array, and I'm iterating back all the way down to 0. So then here I have call a pointer, right? And the reason I do that is because it is already a pointer, so you want to do it that way. And you can see how I have done ampersands with those functions. You do this 32 times, you're going to return the sum, and then I've done 32-bit tests, and then I run it. I do all kinds of functions here, and then I'll do that. So let's start here. I'll start next lecture by going over in more detail how to do 32-bit full adder. Class is dismissed.